In this section, we're going to take a look at some Fourier transform properties. This is going to allow us to see when we, for example, make certain changes to a signal as a function of time, we're going to see what effect those changes have on the Fourier transform or the signal when viewed as a function of frequency. Reviewing from last time, we have that the Fourier transform of a signal is evaluated at the frequency variable omega. And in order to get this complex valued function of our signal x of t, we integrate the signal times this probing function e to the minus j omega t over all time of the function. So what this does for us is it gets us a measure of energy and phase at each frequency of the signal. Now, to construct the signal back, to synthesize the signal from these Fourier components, we do a similar integral, but it has a couple key differences. It has this 1 over 2 pi factor in front. It's an integral, again, from negative infinity to infinity, but this time over the frequency axis, and we take the complex valued function x of omega and e to the plus j omega t. So we see that these transforms look almost identical to each other. They have the difference of this constant factor out front, and they have a difference of plus or minus j in the probing function e to the j omega t. So what this means is mathematically the domain of the function, being time or frequency, t or omega, has a lot of similar properties no matter which direction we're going, from time to frequency or frequency to time. This is going to lead us to a powerful principle that you may remember from circuits called the duality principle. And it means pretty much any fact that we derive has a version in the other domain. And we're going to see some examples of this in this section. We're going to talk about some of the properties in detail, and we will prove some of them, and then we will present a table of properties. Now, when you're working with signals, and this includes, of course, taking a quiz or taking an exam, you will often have a table of most or all of these properties available to you. But it's important that we understand how they come about. So first property we're going to look at is the linearity property. We talked early in the class about what it means for a system to be linear, which means I can take a signal x of t and represent it as two parts, and then I can apply the system to those two parts individually or together. In particular, this was the additivity property. We also had the scaling property. Now, the Fourier transform and inverse transform themselves are linear operations. So not only do we say that the systems that we work with and are of interest are linear, but these transforms themselves are. So if I replace this x of t right here with x1 of t plus x2 of t, so I break the signal down perhaps into more fundamental components, we know that doing an integral itself of a sum of two functions would be the sum of the integral of each of those functions. So each function individually would get multiplied by this e to the minus j omega t and integrated over all time. And so we say that we have a transform pair. x1 of t, when we would transform it, we would call its transform x1 of omega, and we use the capital X to indicate that it's the Fourier transform that goes with the signal small x. And we can also take individually the Fourier transform of x2 of t and get x2 of omega. So that would be doing the integrals separately. And if we add those results together, we get the Fourier transform of the sum of the signal. So that is the linearity property, and we specifically proved the additivity property. This also applies since scaling also works across an integral. So if I scale a signal, I scale its integral. If I put some constants here, let me say C1 and C2, I also have C1 and C2 here. So a constant does not change the fact. So there's the operation is linear. So we have scaling because integral is a scalable operation, and we have additivity because integration is a additive operation. So that's a very simple one, but it's actually very powerful because it means when you have a signal that is composed of summing up several different components, you can analyze them separately and then combine them to get the result. Let's take a look at a property that has a similarly simple statement but is not quite as obvious. This one will be the scaling property, and we're talking about time scaling. Let's start with a signal x of t that is in a pair with Fourier transform x of omega. So we can do the forward transform to get x of omega, and we can do the inverse transform to get from x of omega back to x of t. Now, let's ask what happens if I take the signal and scale its time variable. Then I take the Fourier transform of that, and as I take the Fourier transform here, let's replace the product AT with a variable tau, and then I have e to the minus j, and I have omega. And let's see, what do we have to do with the t? So we have our substitution at is equal to tau, or t itself is equal to tau over a. So we replace t here with tau, and we divide by a, which I'll write right here. And then dt becomes d tau times 1 over a. And in order for the next step, we need to know that a is greater than 0. We'll take the case that a is less than 0 in a minute. So here we have, if I simplify this a bit, I have 1 over a, I pull that term out front, and now I have x of tau integrated d tau with e to the minus j times tau times omega over a. So we see that follows the form of a Fourier transform where the frequency variable omega has been replaced by omega over a. So we get here the Fourier transform with omega replaced by omega over a. If we go through all the steps when a is less than 0, we will get the Fourier transform is negative 1 over a x of omega over a. So let's write that out all together. If I have the signal x at at, so time is scaled by the real number a, then the corresponding Fourier transform is 1 over absolute value of a. So if a was negative, I took the negative, it became positive. So I have absolute value will accomplish that. And in both cases, I had the Fourier transform with omega replaced with omega over a. So if I know that x of t and x of omega form a pair, I know for any real scaling factor a that these two items also form a Fourier transform pair. So let's think about a being greater than 1. That would cause us to speed up or compress time. But look at what happens in frequency. It stretches out the frequency. Let's take a closer look at a specific example that makes use of the scaling property. Here we have figure 5-14 from the textbook, and we have two rectangular pulses, and as we derived last time, when you take the Fourier transform of a rectangular pulse, you end up with a sinc. So I have x1 of t is a pulse with tau centered at 0, so we would call that the rectangular function at t over tau. And now we end up with x1 of omega that corresponds to that is, from last time, tau times the sinc function at omega tau over 2. Remember, sinc is sine of the argument over the argument value itself. So now we see here on the right, when I take the x and expand it, I actually take the Fourier transform and compress it so the edges come in. So this is what the scaling property tells us. It tells us if I expand the signal one way, I compress it the other way. And notice here we've expanded in time by a factor of 3, so the area under that function has increased, and therefore the peak has, in the Fourier domain, has increased by a factor of 3. It was tau before, now it's 3 tau, because our scaling factor A is equal to 1/3. We have A in this case, which has a magnitude positive value and magnitude less than 1, so we expand the function in time, and that compresses it in frequency. That is what the scaling property is showing us. Now let's do the Fourier transform of a fairly simple signal. Let's let x of t be equal to an impulse at t0. So now we will take the Fourier transform of that. So we have x of omega is equal to the integral of that x of t function, delta at t minus t naught, and we multiply that by e to the minus j omega t to move to a function of frequency, integrate dt, and we're integrating from negative infinity to infinity. Here we use the sampling theorem. The sampling property of the impulse tells us that the integrand is 0 almost everywhere. The only place it's not 0 is when t is equal to t0, because that's when the argument of the impulse is 0. So the value of e to the minus j omega t only matters at the point when t equals t0, and the area of the delta is 1, so it does not change or scale what e to the minus j omega t is doing at that time. So the sampling property tells us we take the e to the j omega t and we sample it at t is equal to the location of the impulse. And if we simplify that, the answer is e to the minus j omega t naught. So now we have another transform pair. The transform pair that we have is impulse at t delayed by t naught is e to the minus j omega t naught. Now let's see what happens to this transform pair if I allow t naught to go to 0. If I let t naught go to 0, I just have my input signal x is the delta, the impulse at 0, and the Fourier transform, if I let t naught go to 0, I get e to the minus j times 0, or e to the 0, or 1. Now, Let's see what happens if we try to put the impulses in the frequency domain. Since the Fourier transform and the inverse Fourier transform have very similar integrals that just differ by that 2 pi factor and the plus or minus j, we expect to get a similar pair. So let's see exactly what happens. For a Fourier transform pair here, let's put on the Fourier transform side an impulse. And let's let that impulse occur at some frequency omega naught. This is the dual form of an impulse occurring as a function of time. Now we're saying when I look at the Fourier transform, I will get an impulse, but it's going to be at the frequency omega naught. Now, we're also going to look at the special reduced case when we let omega naught equal 0. So let's figure out what x of t goes on the left side of these arrows. So we now apply the inverse Fourier transform equation, which says I can get the signal x of t back from its Fourier transform. We show that sometimes with the symbol script f with a exponent of -1 to indicate a inverse Fourier transform, and we apply that here to an impulse of the frequency variable. So the impulse occurs at the frequency omega naught. And let's carry the math through. The integral for the inverse Fourier transform is 1 over 2 pi. And we take that impulse and we multiply it. Now, since we're doing the inverse transform, it's e to the plus j omega t. And I have the sampling property again. And the sampling property says that this integral is 0 almost everywhere. The only place it isn't 0 is when omega equals omega naught. And we are left over with the rest of the integrand, e to the plus j omega t, at omega equals omega naught. So we have e to the j omega naught t over 2 pi. So that over 2 pi kind of gets in the way. So let's apply the scaling property of the Fourier transform and just say that we multiplied our starting point by 2 pi. So then when we take the inverse Fourier transform, we'll get something that's 2 pi larger. So we'll get e to the j omega naught t. And now to complete our second line, let's let omega naught go to 0. So I have e to the 0 again, and I have 1. Here we have some dual pairs. We see that an impulse in the time domain at 0 gives us 1 in the frequency domain. Oh, we forgot to write the 2 pi here. Also, we see that conversely, a DC value of 1 in time gives us an impulse in frequency. So this DC value in time that's spread out forever becomes concentrated extremely narrowly into an impulse in the frequency domain. And conversely, if you have something that just occurs at one instant in time and has area 1, it will spread out completely and have all the frequencies in the frequency domain. Here we see if I delay that impulse by t0 seconds, the magnitude of 1 stays the same, but I have changed the angle to omega, which is my frequency variable, times whatever my time delay was. And similarly here, if I take my impulse in frequency and shift it to a frequency omega naught, I still have a time domain signal that has magnitude 1, but now it's a complex number that's oscillating. It has the cosine and the sine components according to Euler's formula. It has magnitude 1, but it has a frequency and its angle is changing with time. Now, we can take this farther. I'm going to give you 2 more properties, and I'm not going to prove them completely, but they're more general cases of what we have just proven. If we look at the blue equations on the top, we see that when we delayed the impulse by t 0 seconds, that its Fourier transform got multiplied by this e to the minus j omega t naught factor. And it turns out that that will happen to any signal. So let's have signal x at t, and it will have Fourier transform capital X at omega. Now if I delay it by t naught, the Fourier transform will get multiplied by e to the minus j omega t naught. What we have up above here is a specific example for a specific signal. But if I substitute this in to the Fourier integral, I can prove that this green statement is true, similar to these other proofs we have done. There is a frequency version of this as well that says if I take the signal x of t and it has Fourier transform x of omega, but I delay or shift that Fourier transform by omega naught, then I have multiplied the signal by e to the j omega naught t. And we have a version of that in the orange formula here. If I take this Fourier transform and shift it by omega naught, I have multiplied the signal by e to the plus j omega naught t. What these green equations are called the time and the frequency shift properties. So here we have the frequency shift and the time shift property. So these are very powerful tools because once we have found the Fourier transform of any signal, all we have to do to find the Fourier transform of a time-shifted version of it is change its phase according to this formula. So as omega increases, we have the phase getting more negative at a rate t naught times omega. And we have a similar relation if I shift the spectrum of a signal, the Fourier transform of a signal, by omega naught, then I don't change the magnitude of the signal, but I do change the phase of its complex value. Now let's use these properties to find the Fourier transform of a signal of interest. Now here, let's take as our signal the cosine at a frequency omega naught and time variable t. Now, normally we have so far thought of our most of our Fourier transform examples of signals that have a period going to infinity, but we've shown a lot of examples where the signal eventually dies out. This signal, however, goes on forever. So let's see what happens with its Fourier transform. So in order to do the Fourier transform, let's see if we can rewrite it using some components for which we already know the Fourier transforms. So Euler's formula comes in handy here. We have the cosine by Euler's formula is e to the j, the phase argument, omega naught t, plus e to the minus j, the phase argument, omega naught t over 2. And now to get the Fourier transform, we apply that to each component here. So we have the first component, e to the j omega naught t. When we Fourier transform that, we get 2 pi times an impulse at the frequency omega naught. And when we do the Fourier transform of the e to the minus j, we have our impulse here, but it's at the frequency negative omega naught. So omega minus negative omega naught, because that's where the impulse is going to be. So omega plus omega naught, divide by 2, and we simplify a bit, and we are left with 2 impulses. Oh, there we go. So if I have the cosine that goes on forever, and then I say, what is the Fourier transform that corresponds to that, I will have impulses at positive omega naught and negative omega naught, and they will have height equal to pi times the amplitude of the cosine. So let's let that be 1 here. So in this particular case, the Fourier transform is completely real valued, and that will happen anytime I have an even signal because the imaginary parts disappear. So the book will take you through some additional proofs that they all have this general flavor. There are some additional tricks of calculus that are used. In some cases, we need to use a limit to get to our answer. But here we have a table showing Fourier transforms for several common signals. Some that we just derived, including the impulse and the time-delayed impulse. And we have also, here we have the DC value, gives us an impulse and frequency. That's an example of duality. So you know, duality says if I see a pattern on one side of the Fourier transform, and I associate with a pattern on the other, here impulse gives me DC value, I can go in the other direction. Impulse over here gives me a DC value here. So that's one of the properties of the Fourier transform. Here we have a unit step, gives us this Fourier transform, has an impulse at 0 due to the DC portion, and then this 1 over j omega term due to the discontinuity. A full proof is in the book. We've already done the proof for the rectangular function, and here are some additional ones. Something that looks very much like a normal distribution. Here we have exponential decay, and the cosine which we just derived. Sine will be very similar, except now we get a pure imaginary Fourier transform. So for a odd signal, you'll get a completely imaginary Fourier transform. And on our final slide here, we have properties. We've proven a few of these. Multiplication by a constant, that's the scaling property. Linearity, time scaling, time and frequency shift we have proven. It can also be proven that if I take the derivative of a signal, I get j omega times its Fourier transform to get the Fourier transform of the derivative signal. And similar with integration from negative infinity to the current time, I have shortcut formulas for that. That's the end of this lecture on section 5.8. We've proven some Fourier transform pairs. We've proven some properties of the Fourier transform. And we've presented the tables that we use to simplify our work with the Fourier transform. So we don't have to do it from scratch every time, but we can see if we make transformations to a signal, we can use these properties to get to the corresponding Fourier transform and also work in reverse.